Hello and welcome back. And we are here again to explore the potential of KiCAD software, which is a free open source electronic design software that we have been using since past few weeks to design variety of circuit and perform numerous analysis, that too with the real world hardware. So we have learned so far how to use the SPICE model for the manufactured parts, including electronic components, devices, and based on that we have demonstrated design, a simulation and analysis of range of electronic circuits. So if you are new here and first time, you are encouraged to refer back to those models to have a deeper understanding about how we have done this and how we have used the KiCAD and the SPICE combination together. So today's focus in this module is to demonstrate you another capability of SPICE. Many a times, oftentimes it can happen that the data sheet of a particular integrated circuits, for example, an operational amplifier would have two parts in a single IC. It means, let's say an operational amplifier will have two parts in an 8-pin package. So how to use those two parts when your schematic needs to use two operational amplifier. For example, on your screen, you see I have used one operational amplifier here. I have used second operational amplifier here. So these two are the different parts, but from the same integrated circuit. And the name of that integrated circuit is labeled as TL072. Here also you see the labeled is TL072. So if you Google this number, you would find this is 8-pin IC of an operational amplifier. You can have a datasheet access just by typing this number on the Google. And in that single IC TL072, you will have two such operational amplifier parts. So I may need to use both of these in some of my circuits. For example, on the screen, I am going to design a band pass filter using Sallen-Key topology. We have covered the Sallen-Key topology second order active filters in our previous models. We have seen second order active Sallen-Key topology based low pass filter, which is right in this section, the two capacitors and the two resistors, and we have got used the op-amp, and we have covered detailed part of this low pass filter in our previous model. Similarly, we just swapped the two resistors positions with the two capacitors position, which looks like this in this part. You see the two resistors have been replaced by the capacitors and two capacitors have been replaced by the resistors, and vice versa. So this becomes then high pass filter. So it is easy to transform the second order active Sallen-Key high pass filter to second order active Sallen-Key low pass filter and vice versa, but just by swapping the positions of resistors and the capacitors. So today's focus is to design the circuit and simulate through various analysis using KiCAD software and understand the performance of a band pass filter. So as I said, you can refer back to previous module to understand how to pick up all these components and the devices and the ICs symbols from the library. For example, I would like to show you by clicking add symbols here, and after clicking this add symbol part, it it opens this box, which is a choose symbol box. Here I have typed TL072, and with that uh, I found this is an operational amplifier, which is a general operational amplifier. So it says TL072 is a dual low noise JFET input op-amp. It comes in the package of DIP8 and SOIC8. So I clicked here then and I found it has got three parts. So unit A is looking like here. then unit B is 5, 6, 7 is like here, and the units in C are the power supply pins. So what I did, I have recently used this, what I showed you in the schematic. That's why this is reflecting here and already placed or recently used. That's why. Otherwise, you will do it for the first time, then you will have such things part. So I clicked on unit A and I clicked OK. And when I clicked OK, you see now I got this first part which I placed here. When I moved, I got the second part with the pin 5, 6, 7 here, and then I moved, I got the third part which is the power supply pins. And you see now around that red laser spot there is a simple op-amp symbol. To get rid of it, I will press escape button on my keyboard of the laptop, and this is how I created these two parts. So it is, I am just showing it to you again how I got this TL072 from the KiCAD library. So I will now click them again and delete it because I have already used it from the library and I have successfully placed these parts in the schematic. So once that is done, I already have shown in our previous model, you just can search for capacitors, you just search for resistors, place them, rotate them, and we have covered it all before. After placing them, you can double click on any of the component and specify the value in the edit value field. Okay. Similarly, we have also shown we are using here plus minus 15-volt power supply pins for these ICs. So pin number 8 and pin number 4 as VDD and VSS respectively of this part TL072. If you want to have a detailed information about if it's as it is a JFET input dual low noise amplifier, you can access a data sheet. You can get wealth of information from the data sheet. You can just type the number in the Google and you can get access to how much is the offset voltage, how much is the power consumption, how much is the bias current, CMRR, PSRR, maximum supply voltages that you can use, so on and so forth. So all this information, if you are critically designing or optimizing your electronic design for those specifications, to meet those specifications, you need to refer to the data sheet. Okay, but for now, we are keeping our discussion limited to the design and development and simulation of the band pass filter using Sallen key topology. For that, this is our high pass response, this is our low pass. By combining these two together, we are trying to create a band pass response. So power supply flag, all these symbols, we have explained why you are needing them, how you are needing them, how to access them from the library, and how to place them. We have covered it all in previous models. So let us now focus upon the schematic. Now I have applied a sinusoidal voltage source, which can be a DC voltage source, sinusoidal voltage source, and AC voltage source, depends on what analysis I want to perform. So I will specify based on that. So currently I am using a sine wave voltage signal here with a peak amplitude of 100 millivolt and the frequency of 50 kilohertz. That is my signal frequency, 50 kilohertz. You can specify based on your. So band pass filter, as we know, it will have a band pass response where you will have a specified band pass band of the frequencies where signals are allowed to pass through the filters, and on the other ends of these pass bands you will have attenuation of your signal. So that's the basically a band pass filter, how it works. Okay, so now once that is done, since this is a real world part, that is the real hardware TL072, I am going to need a spice model for this one. So what I have done is I have just typed spice model TL070, such a phrase on the Google website. Once I type that, I got access to the manufacturer website. From the manufacturer website, I just downloaded a zip folder of this spice model. That zip folder I am going to show you. It is in the download folder, and when I unzip that, this was my zip folder, and when I unzipped it, I got access to this folder. Now in this in this unzip folder, I had this only one file. I will show you why this second file is coming here and how it is coming here. So I have got the access to this first file, which is a kind of the type of the file is a 301, as you can see on the screen, the type, size, and date modified. So 301 is the file type. In fact, in our previous model, we needed a spice model, and we usually had the extension of the model file as a .lib file, for example, here. Or for example, let me show you in this folder, we have used few of these op-amp models, and if you just scroll over your mouse, you see that there is a type lib here. Okay, here if you see, there is a type lib. So lib file is what you needed, but this is the first time I'm going to show you. Let me take you to download folder, and in the download folder, like I said, this is the unzipped file. I had got only this file, and I double click it and I saw this is a spice model provided by the manufacturer for the part TL070 op-amp. So this is the operational amplifier macro model given by the manufacturer. Look at the sub-circuit, how this sub-circuit is called into the spice, into the ngSpice or simply spice or KiCAD. So it is called by this command dot sub-circuit, the name of the part, and then the sequence of the pin. Pin number 1 is non-inverting input, 2 is inverting input, 3 is positive power supply, 4 is negative power supply, and 5 is output. And then you've got the capacitors, diode, resistors, everything around to finally. And then there is this diode model. Then there is this dot model JX again. Okay, what is this component? You need to, maybe we need to find it. And finally, this sub-circuit or micro model ends with the dot ends command, right? So now you see this sub-circuit has got only 5 pins, but in our schematic, oh, let me show you the schematic right here. We are needing a total 8 pins. Why? Because we have used 2 op-amps. So each op-amp uses 3 pins. Here 3 pins, 1, 2, 3, then 5, 6, 7, total 6 pins, and 2 pins are of power supply, 4 and 8 are VSS and BDD respectively. So total we are in a need of 8 pins, but the sub-circuit of this part has only 5 pins. So what you need to do, we need to call this spice model twice in this circuit. That is the first point, because we have defined this spice model twice, this one and this one. So what you need to do here is you need to additionally create an empty notepad, open the empty notepad, and then write this code in that notepad. So what is this code? This asterisk sign says that this is a comment only. This is not a command, rather it is a comment. So it is a dual op-amp ngSpice model. Then file name is .lib. Now this is a .lib file that we need to call. Okay. And in fact, this .lib file has to be stored in the same folder where you have stored a spice model. That's why you are seeing here, I have stored this TL0C-dual.lib file, and I just stored it in the same folder where my spice model is. Okay, so what I'm gonna do show you is that you see that how I now call it. I call it with this command dot sub-circuit, then part name, then first pin is, that is the first part, out pin, in minus pin, in plus pin of the first part, then positive supply, the negative supply, VCC minus, then second in plus pin, second in minus pin, and second output pin, and then the VCC. So this is the fixed sequence that I need to, and then I would say dot include TL07172, TL072.301. So this command dot include will include this file, which is right here. You see the extension of this file is 301. Okay, that's why we have included. And then after that, I am using this, calling those instantiation. This is called instantiation procedure. That is just mapping the sub-circuit on those pins of the KiCAD symbols. So here X says I am instantiation the sub-circuit. So XU1A part, XU1B part. So I have used in the KiCAD two parts A and B, and that is what I am doing. So first pin is in plus, second pin is in minus, then comes positive supply pin, negative supply pin, and then finally is the output, and then there's the part name. You see the sequence: in plus, in minus, positive supply, negative supply, and the out. Where do we see it is? So let me show you. Where do we see this? Right here. If you see that, this is the pin sequence. First is non-inverting, that is the positive pin, then the negative pin, then the positive supply, then the negative supply, and then the output. Because this is specified like this, here I have specified positive pin, positive supply, negative supply, and then the out of the first part. And this is also then the second part the same, because I have used. And then I will dot end, click here, save as, and after I click the save as, go to download section, and this is how I have done that. I have used that, and I will say that just select this and repeat it. Okay, replace it. Okay, if you are doing it first time, make sure it has a extension .lib. That's it. Once that is done, what I have done, I have come back to my schematic. Okay, when I have come back to my schematic, I have double clicked this part, and then I click the simulation model. Then this field was empty actually. These two fields were empty. Then I click the folder, and then I went here, and then out of this file I need a .lib file. So I selected that, I clicked open, and it got there. Then this, I clicked on this model and I selected this one, and that's it. Once that is done, I clicked OK, and now I can actually click again the simulation model, and then I click the pin assignment and look at this pin. Symbol pins now, which you see on the schematic, and then there are the model pins which you see in your model files. Okay, in your model file is the .lib file. Look at this .lib file. Look at the pin: out, in minus, in plus, VCC, in plus, in minus, out, VCC. So here symbol pin 1, if you recall, this is your output pin in the symbol, and model pin also, it is an output pin. Then symbol pin is the negative pin. Then here the model pin is the negative pin also. So there is a perfect mapping, which we have explained you in our previous model, how to do this mapping, but this has got automatically, and this is how it will be mentioned. So if you want to understand this mapping in a detailed fashion, then you are encouraged to refer back to previous model. Okay, so I will just click OK now. I will click OK here, and all set. We are all set now to run the simulation. So let me show you that step by step. So everything is set now. We have very well covered the SPICE modeling part, and calling it into sub-circuits, and calling sub-circuit twice. And once that is done, circuit is ready. As I said, this is a high pass filter and this is a low pass filter, and cascading the two will form the response of a band pass filter. So what we can do is first go for electrical rule check, that is ERC. Click here. I have done it before, so I have got 0 errors and warnings. So I'll not take care of warnings, I'll just ignore. But for you, I'll click here, run again, and I see 0 errors. That is what I want. And warnings is about this. This is not that important because I have copy pasted this schematic from my earlier schematic. So most likely those warnings about the libraries are highlighted, but that's not gonna interrupt or intervene in my simulation and the results altogether. So I will just click zoom to objects. I got back a proper view now. And then I go for simulator right here. Okay, so simulator, when I click it, it opens this window. Then I need to click here, new analysis. Once I click that, I get this tab. I can see the new simulation tab. So operating point analysis, many analyses I have available. So we have done many of them in our previous module. So we'll start with AC signal. Number of points, let's say 1000. Start frequency is 1 hertz, almost DC we are starting with. And then let's say this is like 1000 or say 100 kilohertz. That's it. You need to know what your bandpass range is. Otherwise, you will end up with like unknown parameters. So you need to know by theory calculations what your parameters are. So click run. Once you click run, then you can see on schematic what you are interested to plot. So here I have labeled it as a VO1. Here I have labeled it as a VO2. So VO1 is the response of a high pass section, and VO2 is the response of a total circuit, that is a band pass. So we'll check if that comes. So VO1 is here. So look at this. You see that I have attenuation in a negative, and the gain is 0. That is, gain is 1, 0 in dB, and the gain is 1 at around after 100 hertz. So about 200 hertz. From 200 hertz up to 100K, I have a constant gain of 1. That's what I have, because op-amp is configured as a non-inverting buffer. It's a voltage follower. We don't have a gain offered by op-amp. So that's it. And then if I want to plot phase, is what you see, this red curve. Maybe, yeah, it starts from like minus 180 or plus 180 all the way, and it is like a 0 degree phase shift here. It's a 0 degree. Then my final output is right here, VO2. Look at this, a very good band pass. So here is your first cutoff frequency, and here is your second cutoff frequency. The pass band is from, let's say, 70 hertz to about 2 kilohertz. Okay, that's the pass band. And then you have a sharp notches on the either side of this response. So that's your band pass response. You might want to modify, click here. And then after clicking, you just say, I want like 1000K. I want to simulate up to 1000K. So click over, okay. Then click here and look at this. It's still the same, but then you extend for a higher frequency. The response looks like this. There is a notch and then again, but there is still a higher attenuation. But the high pass response looks clean. So that is how you can go. So pass band is from, let's say, few tens of hertz up to here, 2 kilohertz, right? So if you perform the time domain analysis now with a 50 kilohertz, obviously you will have a heavy attenuation. You want to try that? See that. Let's see that. So we have got like 50 kilohertz. And if we do the time domain analysis, like click here, transient analysis, time step is like, let's say 1 micron. Yeah, 1 micron enough. Then your final time is, let's say, 100 micron, maybe. Initial time, leave it like this. And then simulate. And we'll first see how the input looks like. So input is, yes, is 100 millivolt signal. Do you see that? Peak volt, yes, that's good. And then what about VO1? High pass, that's okay, because 50 kilohertz high pass frequency, your gain is 1, input is output, output and inputs are equal. So that's fine. But what about VO2, which is your final output, a band pass? Will there be light? And VO1, VO2 here. Look at this, heavily attenuated. The signal got heavily attenuated because you can't use the 50 kilohertz signal. How about, let's say, 500 hertz maybe, or 5 kilohertz? 5 kilohertz should be okay, although we have like 2 kilohertz cutoff frequency at the higher end, but we'll try that. But it is likely here also you will have some attenuation. The gain won't be equal to 1. That is what you see here. You see, the red and blue are okay, but the green is reaching up to this peak, this signal only, this one. So that's the maximum signal of about 18 millivolt, 18 millivolt right here. But you want 100 millivolts. That's it. What about 500 hertz? 500 hertz or maybe 1 kilohertz would be better. That's what we saw. So 1 kilohertz will be close to 1 now. The gain will be close to 1. We'll see that. We'll see that. And yeah, I mean, not too close still, but you can see that. But what you can modify here, just instead of the time span of about, let's say 100 micro, maybe you want to do like say 1000 micro or 1 milli. That's the what better thing. Better thing you can do 1 millisecond. Now look at this. You got this. There is a little phase shift though between green and the red lines, but your green is now close to 1, right? So peak to. So this is how you can simulate range of analysis and see your band pass response. Play with the values here. For example, you change the values here of about say 220, so let's say 110 nano, for example, and you will see you will have like uh, change in your response 110 nano, not 120, but 110 nano. Okay. Once that is done, come back to simulation. Now, with time domain, you won't know what is your band pass frequency range. Instead, you will click on AC simulation, hit run, and see how it changes. Does it change? A little bit maybe, but you won't see. Yeah, you see now this the pass band is narrowed, starting from like 200 hertz, and it is ending up it here 2 kilohertz. Now, and you can use the tuning factor also, a tuned value. For example, not a high pass. I would be interested in C3 change and maybe, yeah, C3 and C4 maybe, and come back to this screen and then maybe look at this. If I change this, look at this, the shape is changing. Your things are changing right here. Yeah, this is how you can modify and all these things. Okay, so try with different analysis on your own and hope you found the design useful and understood the response of a band pass. One thing I forgot to show you is like you can click hit and export current plot as PNG. So you can just say save it anywhere with some name right here and save it. That's it. With the transient also, you can just click file simulation, export as PNG, and then give it some name and then just save it in the folder of your choice. That's it. So with that, we stop here. Hope you found this module useful. If you did so, share it with others for a wider range. Stay tuned for more engaging content like this. Till then, wish you happy learning.